Okay, welcome to the Henstitute. After having created the MegaWork energy equation, I want to see if we can try to take a look at using it. So in this particular example problem, if we start off, we know that work is going to cause a change in kinetic energy. It can cause a change in gravitational potential energy, or it can cause a change in elastic potential energy. Now, in a lot of our problems, we don't actually have all these parts happening to it. So I've got two parts of this. One, I'm trying to figure out how fast this block is going to be going at point B, which is right here. And the other one is we're going to try to figure out how far the block is sliding between points C and D. So as I try to do that, and that's going to go from C to D over here, we're going to see if we can kind of go after this. The first part is work is only going to happen if we have some kind of force happening over some kind of displacement. And I'm going to get rid of the cosine theta part for right now, just because most of the time we're going to have the force that's going to be in the same direction as our displacement or in the opposite direction. So we're going to have either a positive or negative value for that. And then we have our change in kinetic energy here, which is going to be 1/2 the mass of the object times its final velocity squared minus the initial velocity squared. So we'll have that part. Then we're going to add to it the change in gravitational potential energy, which would be mass times gravity times our change in height. So final height minus initial height. And then last but not least, our elastic potential energy, which is going to kind of look like our kinetic over here. So it's got a 1/2, but it's going to be the spring constant, that thing that we've been working with Hooke's law. And then we're going to be multiplying that by some final compression or stretch of a spring. So this is supposed to be an XF minus an initial compression or stretch of a spring. And those are both quantity squared. Now, as I kind of go through this, the first thing I always do with MegaWork energy problems is I eliminate stuff that I'm not going to be using. So as I look at this particular problem, is there any springs that you can see or any elastic materials you can see here? I've got ice all the way down here. So this is all ice. I don't have anything here. And then over here, I have some rough surface. They do actually mention that this rough surface between C and D has some kind of friction acting on it. Whereas our ice section, so we have an ice ramp, and then it skids, the coefficient of friction between there. We're going to assume the ice ramp is frictionless. So I don't see anything that has anything with springs. So what that means is we can actually cancel all of this. We don't need to use that at all. So just to make this a little bit easier on myself, what I'm going to do is I'm going to actually erase this part of the equation, and we'll just get rid of it. It doesn't mean that it's not there. It just means for this particular problem, we don't need it. So might as well simplify our situation. So I'm going to start off with part A. If I'm trying to figure out how fast the block is going at point B from point A, what we've got is the object is starting up here at point A. It's going to slide down this ramp like so to point B down here. So this is going to be the path of it. During this, do I have some kind of change in velocity? I would say yes, I probably do, because up here at the top, it says that the initial velocity is 1 meter per second. So I do know that initially up here, it's going 1 meter per second. We're trying to find how fast it's going at point B. So we're really trying to find that final velocity. So that's definitely going to be a part where we have a change in kinetic energy. The other part is, do I have a change in gravitational potential energy? So in other words, do I have a change in height here? And sure enough, we're up here at point B, and we're going to drop down here to point B. Whoops, we're up here at point A is what I meant. We're going to drop down here at point B. So that's definitely a change in height that we have going on. I know we're going this diagonal distance down the ramp, but for right now, I don't really care about that. It says this block is 20 meters above point B and 15 meters above C and D. Right now, I'm not worried about C and D. So I know that this initial height would be 20 meters. So one of the things I can do is we often like to set some kind of initial position. So if I kind of consider this a height of 0. In other words, this is kind of my low point. What it allows me to do is actually say that the final height of this object is actually going to be 0. So that's going to be kind of nice. It's going to mean that this part of the equation will end up being 0. The other part is, do I have any work happening on this object? In other words, is there a force or a displacement? Is there any kind of work going on? Well, between point A and B, I don't actually have any work because the ice ramp is frictionless down here. So if it's frictionless, this means that there's no force acting on it. Now, this is always kind of misleading for people because they go, wait a second, there's gravity acting on it. Gravity is a force. And I say, yes, that is true, but we have already taken into account gravity in this part of the equation. So the G in GPE stands for gravitational potential energy. I'm talking about other forces acting on it, whether it's the wind, whether it's air resistance, whether it is, which are basically the same thing, whether it is a force due to friction, if it's some kind of external force acting on it that is not gravity, and it's not going to happen by a spring because we would have gotten rid of that. So friction is going to be the most common, and therefore we don't actually have any force. So the force is equal to 0, or in other words, this entire quantity over here is also equal to 0. So here's what I get to do is I really have just my 1/2, I'm going to write this in red, my 1/2 m times Vf squared minus Vi squared plus, change over to green, I have mass times gravity times, I got rid of the initial, or the final height to 0, so I have a negative HI that I'm solving for. So really what I'm going to end up doing is trying to solve for this. Here's the cool part. They did actually give us the mass of the object. So it's a 5 kilogram object. But if you actually look at this equation, if you notice, the mass would actually cancel from this equation. I can actually get rid of the mass. And therefore, when I solve this, I bring one part over to the other side. So I would take this part and add it to the other side of the equation. And what I should end up with is, since I'm adding that, I'm going to have G times HI on the left side. And then over here on the right side, I have what I have left. I have this 1/2 final velocity squared minus a 1/2 times my initial velocity squared. Now I can plug in my numbers and solve for Vf. I know the acceleration of gravity is going to be 9.8. So as I solve this, I'm going to end up with 9.8. My initial height was 20. And then I'm going to set that equal to 1/2. I'm trying to solve for the final velocity, so there's going to be my Vf minus my initial velocity, which was 1, and that quantity is squared, though 1 squared doesn't really change anything. 9.8 times 20 is going to give me 1,960, because I'm going to move it 2 places over. Well, 2 times 9.8 is 19.6, and then I move it over 1, and so we should be able to get that. Then over here, I have 1/2 Vf squared minus 1/2 times 1 squared, so that's just minus 1/2. And then I just have to solve for Vf here, and Vf should be, oh, I made a mistake here. 9.8 times 20 is not 1,960, it's just 196. So I'm going to get rid of that 0 there. Sorry about that. And so when I add this 1.5 or this 0.5 here, this 1/2, it's going to be 196.5 equals the 1/2 Vf squared. So then I multiplied by 2, so that means Vf squared is equal to 393. I was typing some of these numbers in, and my final velocity here would be 19.8 meters per second. And that tells me how fast this object is going at point B. This is a very useful one. This is a very common idea that we can actually find how fast something's going when we don't have any external work being done, and we really just have our change in kinetic energy coming from a change in gravitational potential energy. So that's what we're going to start off with. That allows us to find part A. I'm going to post this, and then I'm going to come back and I'm going to solve for part B as a separate problem. So hang on, and I'll be back at the Henstitute.